Hi everybody, welcome to another Chem Complete episode. We're going to continue general chemistry today. We're going to be looking at the quantum theory, and in particular we're going to take a look at electron shells and quantum numbers today and attempt to make sense of these quantum numbers, what they mean, how I can utilize them, because they come up very often in general chemistry classes. So let's get started on that. So there are four major quantum numbers that you need to recognize or understand. And these are the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the electron spin number. So all four of these are sets of numbers that can be used to identify or give uniqueness to each individual electron. And hopefully we'll tie all this together and it'll make sense towards the end of this lecture. But first, there are some rules that govern these four numbers. We need to define them, and then we can put them in the context of individual examples and make sense of them. So, the principal quantum number can be represented by the letter N. The angular momentum quantum number is represented by a lowercase l. The magnetic spin number is represented by m sub l. And the electron spin is represented by m sub s. Both of these really have to do with magnetics. Electrons have opposite spins and they behave as their own little tiny magnets. So the principal quantum number, you can kind of view each of these as though they were getting more and more specific about an electron. So think of it like an address for an electron, right? This would potentially be the state that the electron lives in. This would be the zip code, so then we're getting to a specific part of the state. And this would be the street and the house address. So on that street, now we're narrowing it down, so the street number. And then this would be the individual that lives there, right? Because we're going to have multiple people that could live in a household. So in the case of electrons, there's always two people per a given orbital, or two electrons per given orbital, not people. And those would be represented down at the most basic level of the electron spin here. So the principal quantum number is the state that you're in terms of your quantum level. So remember, if you saw the Bohr's atom video, and I would suggest you go back and view that if you haven't seen that yet, but we talked about when we were looking at electron energy levels, we said n equals 1, n equals 2. It's your principal quantum level, or what shell, valence shell, are we currently in and working with. And so principal quantum number, n, deals with that. And the lowest you can have is a quantum number of 1, but it could be 1, 2, 3, 4, etc., okay, as long as it's a whole numbered integer. So I'll just put etc. there. So I jump up in these quantized levels. Now, that's the first one. That's probably the easiest one to understand when you're working with the elements and atoms on the periodic table. Now, the angular momentum number has to do with the specific orbital we find ourselves in. And just to remind you, I don't know if you've gone over this a whole lot in your class, but S, P, D, and F are the different orbitals that we have available. Those are the types. So S is spherical in nature. It's a sphere. P is sort of this dumbbell shaped. So here's an S orbital. Okay. Here's a p orbital, one of the several p orbitals. And then you have d orbitals, which are getting even more complex. I'm not going to draw this very well, okay? And then f orbitals, I'm not even going to attempt to draw an f orbital right now. But you have increase in complexity in your orbitals when you move up this way. L is going to represent what orbital you have. So L can start at 0, and it can go up to n minus 1, where n is your principal quantum number. So if my n is 1, then L can only be 0. If my n is 2, then L could be 0 or 1. If my n is 3, L could be 0, 1, or 2, so on and so forth. All right, now what's important to understand here is that S equates to 0, P equates to 1, D equates to 2, and F equates to 3. So you're usually not going to go much above 3 when you're dealing with your angular momentum value. 3, the f orbitals, that's going to be down with like the lanthanide series, the large part of the chart you always see removed underneath the periodic table. But we tend not to go much past that. So the magnetic number is going to range, m sub L can range from negative L to positive L. Okay, so whatever L is, if you decide L is 2, then your values can be negative 2, negative 1, 0, 1, and 2. And this really represents, if these represented the shells up here, or we can call these the orbitals, because that's the proper name, right? If L represents the orbitals, then M sub L represents the suborbitals. And that'll be a little more clear in a moment, but essentially what I'm talking about is take a p orbital, for instance. There are 3 different sets of p orbitals, px, py, and pz. So if you are dealing with a quantum momentum number of 1 and you're identifying a p orbital, then the question is, are you in px, py, or pz? Negative 1, 0, or 1. Those are the ranges that you could have there. So that is how the suborbital orientation works in terms of those numbers. And then m sub s is actually very simple. It's plus 1/2 or minus 1/2. Those are the only 2 options we have when we deal with the electron spin. So once you get into an individual suborbital, every suborbital can only hold 2 electrons, and therefore it's either a plus 1/2 electron spin up or a minus 1/2 electron spin down. And this is going to lead into, we're not quite there yet, but the next lecture we'll start talking about orbital diagrams. And that will become important there as we start to discuss that. So let me go ahead and clear. That just cleared part of that. Clear everything. Nope. All right, let's try new. Don't save. All right, there we go. So what we are talking about here, let me bring up the periodic table, which I do have in my clipboard, so paste that there. All right, so you have the periodic table here. Don't want to get too large. All right, now most people should be pretty familiar with this, hopefully, if you're in chemistry. So here's the periodic table. The location of the s orbitals, let's get back to my, there we go. Okay. Location of the s orbitals are these first 2 over here. So this block right here, those are the s orbitals. The p orbitals are anything from group 3a, which is over here, to the end of the periodic table where I find the noble gases, right? And let me move my fantastic talking head to the middle here so it makes more sense. All right, so this is going to be where I would find the p orbitals. The section right down here, which we know is the transition metals, these are going to represent the d orbitals. And then over here, down in this section, these would be the f orbitals, keeping in mind that they would be placed in right here. So this is a separation in the periodic table so that it doesn't extend so far. We kind of cut that out and put it down here, but these would be your f orbitals. All right? So you can only have one type of s orbital. And that makes sense. Think about it in the 3-dimensional sense. A sphere is just a sphere in 3 dimensions. So it doesn't matter how I turn it, how I orient it in 3 dimensions. It only is going to have one orientation, which is the sphere itself. So s orbitals, right, are found over here. And again, you can see there would be 1 electron and another electron like that. So those are your s orbitals. Okay? Here are your p orbitals over here. So I have a total of 6 electrons that I can place into these p orbitals at 2 apiece. So I have px that would be going along this way, right? Px, and then I would have py, and it's not the easiest to draw here, but I would have pz. Pz would be going through px and py think about 3 dimensions, right? You have an x plane, a y plane. If it's just x and y, that's 2-dimensional, like a graph. To make it 3-dimensional, you have to have PZ, which is coming into and out of the plane. But those would be the 3 potential orientations you have here. So when you're looking at this, these guys right here, right, would be the 3 different p orbitals that you could have. And then D, you would have a potential of 5. So here's 1, because 2 electrons per. Here's 2, here's 3, here's 4, here's 5. And then for the F, you would have 1, 2, 3, 4, 5, 6, 7. All right. And then when you get to that point, you're returning back up here to the d orbital when you get there. So when you are working with this, right, these are the different areas of the periodic table that refer to a given orbital. So you have s orbitals, you have p orbitals, you have d orbitals, so on and so forth. So that's important to understand. So let's take an example. Let's say we want to look at the electron in hydrogen, right? That's a good one to start with, because hydrogen should only have 1 electron in its normal state. So let me move this back over. All right, so hydrogen would be in what level? Well, if I paste my periodic table here, I'm going to keep it smaller down here at this point. All right, hydrogen, here's when you're looking at this stuff, this would be n equals 1 right here. This would be n equals 2. This would be n equals 3, n equals 4, right? So on and so forth. So hydrogen, the n is going to equal 1, right? And this would be the different quantum numbers that I'm working with here for a hydrogen atom. So the electron there's only 1 electron. It would be in n equals 1. Remember, the rule for L is 0 up to n minus 1. Well, 1 minus 1 is 0. That also makes sense because an s orbital is 0, and hydrogen is found in an s orbital. I also want to just note here, helium is an exception to this. Helium is not found in a p orbital. This also belongs with hydrogen for an s. The weird thing about the n equals 1 is it only needs 2 valence electrons to be complete. So they do consider helium to be a noble gas because it has a complete outer shell. It wouldn't really make as much sense putting it right here, because then it's trying to attempt to equate it to one of the alkaline earth metals that we have here, and that's not how it behaves. So it's put over here in the realm where I would normally see P, but just keep that in mind for helium. Okay. So M sub L can range from negative L to positive L. Well, that's 0 in that case, because 0 doesn't really have a positive negative range, it's just 0. And then you have M sub S, and M sub S is going to equal, well, it depends. If I look at hydrogen, is my electron spin up? If it is, then M sub S is plus 1/2. If not, then the spin down would be minus 1/2. So it's going to be one of those two depending on what you have present. And you half your hydrogens could be spin up, the other half could be spin down. So statistically, it's 50-50. But from the conventional standpoint, the way we normally write is if we have an empty orbital, most chemists will put a spin up electron when they start to fill it. All right, so let's take a look at one more here. I'm going to probably break this into 2 different lectures just because this could take a while and I don't want to have like a 40-minute video or whatever. So let's take a look at one more here. Let's clear. All right, and let's take a look at, I think we'll do something like nitrogen. Okay, so paste. So we've got this here. Now part of what you have to understand as you're working with this is how orbital diagrams work. All right, so we're going to get to that. That's in the next lecture. But for right now, I'm just going to show you. All right, I've got, if I have nitrogen, here is n equals 1. Right? So n equals 1 only has an s orbital. So here's n equals 1 is going to just be the s orbital. And then when I get to n equals 2, which is now down here, I have the 2s orbital. But then over here in row 2, I also have a p orbital. So the p orbitals, remember there's 3 of them. I'm going to have px, py, and pz. All right, now this is the best way that I can explain this as I'm drawing this out here. So hopefully this makes sense. So here's nitrogen, right? So if I started filling up electrons, I'd have 1, 2, 3, right? Counting 4, 5, 6, and then nitrogen is 7. So I have 7 electrons to work with. I should always place them into the lower energy orbital first, meaning n equals 1 would contain 2 electrons, and then once it's full, I can move up. There's a technical term for this, but we're going to talk about that in the next video where we start doing more electron configurations and orbital diagrams. But for right now, all you need to know is that you're going to fill these up in order of energy. So here's S. I've used 4 electrons. Now when I get here, these are all equal in energy. Px, Py, and Pz are equal in energy. And so I'm going to put 1 electron in each before I would start pairing them together. So one of the things we could look at here is what are the quantum numbers for each of these electrons, for this one, and for this one, right? All 3 of them. So let's take a look at that first one. Well, we are in what quantum level for this particular electron? We're in n equals 2. So for the first electron, n is going to equal 2. So what is L going to equal? Well, L can equal 0 or 1 because 2 minus 1 is 1. So remember, it's 0 up to n minus 1. So L, in this case, is going to equal 1 because I'm dealing with a p orbital. So the S would be an L equals 0. The P would be an L equals 1. And so this is L equals 1 if I'm dealing with this electron. Now M sub L, we haven't really seen an example where the M sub L gets differentiated yet. So here we go. If I look at this, and I'm kind of arbitrarily assigning this, right? What I'm saying is -1 right here, 0 right here, and 1 assigned to each of these. So in this case, this guy is found in -1, in subshell -1. And it is spin up. So the M sub S is going to be +1/2. Okay. Now, what about this one, this next one? Well, it is also in n equals 2. The L would also be 1. The M sub L this time would be 0 because I'm in this middle one here. And then the M sub S would be equal to +1/2. Okay, and hopefully you can see the same thing over here. I'm going to have the same N, the same L. My M sub L in this case is going to equal 1. And then my M S would equal 1/2, +1/2, because these are all spin up, right? So let me give you just one more, and then I'm going to cut off this video here, and I will work on a second part where we can, maybe we'll probably talk a little bit more about it, but we'll also get some practice in, some more practice. So it's clear. All right. So bringing in the periodic table again. If I take a look at this periodic table, let's look at the electron in aluminum, okay, the last electron in aluminum. So if I wanted to do that, here's aluminum. It's got 13 electrons. So here's n equals 1. Remember, I have to pass through these quantum levels before I get to aluminum. So I'm going to say 1s because it is an S shell, right? And then I come down to quantum level 2, and I have 2s, and I also have a 2p. Remember, There's 6 electrons total throughout the p realm, which is over here. Here's p, here's s. And so I need 3 of these different orbitals. Then I come down here, n equals 3 is going to be 3s to start with, right? And then 3p is where I find aluminum. In fact, aluminum is at the very beginning of 3p. So if I filled these up, right, I would do it this way. I'd say all of these have electrons. This has electrons. And what I'm doing here, I'm creating orbital diagrams. So we're going to be talking about this in the next lecture. But what I have here is, let's take a look at this electron right here. Right? So this electron, if I wanted to refer to it, it would be n equals 3, because it's in the 3rd quantum level. The shell, or the orbital, is a p, so that's going to make it 1. And the m sub l in this case, well, I find it in the first of the 3, so I'd make this -1, 0, and 1. So that's going to be -1. And then the m sub s would be equal to +1/2, because it's spin up. So let's do a spin down example, just so we can see. So let's say we're interested in this electron right here, right? So what are the quantum numbers for this electron here? Well, it's found in a 2p orbital, so n equals 2. Again, p is going to be l equals 1. The suborbital here, if I have -1, 0, and 1, is going to make m sub l equal 0. And then m sub s, because I finally picked out a spin down, is going to be -1/2. And so what you should be able to see is no 2 electrons are going to have the same 4 quantum numbers. Right? So if I take a look, even if I go to this one, 3 of them would be the same, but now this is spin up, so this changes to +1/2 for that other electron that's to the left of it. So these are quantum numbers. They're used to identify electrons, and we can arrange these electrons into diagrams. So in the next lesson, I would like to take a look at electron diagrams, and then we'll tie in some more quantum numbers and discuss that. So I'm definitely going to cut the video off here because we're at 20 minutes, 22 minutes actually, and I will see you guys for the next lecture. Please remember to like, comment, and subscribe, and I will see you there. Take care, guys.